So this will be forces lecture number 2, and what you're required to do is to summarize the key ideas, concepts, and formulas that will be presented in this lecture. After you have done so, you will receive a done stamp for the day. Now, all forces are not the same, and they can be classified in two very broad categories, and that is contact forces and what we call field forces. Now, a contact force basically means that the object and the force have to be touching. Think about contact is touching. So the thing that is causing the force has to be in contact with the object. For example, tension. You have to be touching the rope or the chain. The object has to be touching the rope or the chain that is applying the force in order for the force to be a force. So tension is very definitely a contact where you have to be tied to or touching a rope or a chain. The normal force is very definitely a contact force because you have to be contacting that surface. Without any contact between the surface, say this pen, it is not in contact with the table, so therefore the table can't be pushing back against it with a normal force. So normal force, tension, and some others that we're going to look at are examples of contact forces. Any force that is applied by a person is called a contact or an applied force. If you and I push on something to move a couch, say, across the room, that's an example of a contact force. So all forces that come from people, unless you're a Jedi and you're exerting the force through open space, are contact forces. On the other hand, field forces are applied through open space without any need to be in contact. Now, some examples of field forces. One is gravitational force. We know that the Earth has gravity and it exerts a gravitational force and it pulls in things like asteroids. Well, they're not touching the asteroids. Therefore, gravitational force is a field force. And by extension, so is weight, because weight is the effect of the gravitational force on an object. Okay. Now, there are some others that we're not going to get into right now, but think about electrical forces. Electricity can have a push or a pull on objects, but it's exerted through open space. Same thing with magnetism. If you've ever had two magnets, you start to get them close together and they pull together, or they won't touch one another, they push apart. Well, they've never touched each other. That's an example of a field force. Now I want you to think about an object, say just a regular block. And let's consider drawing a free body diagram of this block sitting on this paper. Well, what forces are present? We know that there is a weight force going down. And let's say here I've got it listed as 1 Newton. Well, it's not moving, therefore there must be an equal and opposite force because it is in equilibrium. So the net force must be 0. There must be a force pushing back that is also 1 Newton. What is that force? In this case, it's on the surface of contact. It must be the normal force. Very well established. But piggybacking off of what we did with our drawing free body diagrams yesterday, let's apply another force. Let's say I'm going to start pushing on the block this way, and I'm applying a little bit of force. Well, that's an applied force, and it's going this direction. And it doesn't matter how big I draw this arrow. Let's say that's the magnitude of my applied force. I'm not doing it with a spring scale, so I can't actually put a number on this. But you'll notice the block is not changing its motion. It hasn't moved, even though now there is another force going this way. That means there must be an equal and opposite force going this direction. The question is, what force is that? We know it has to be there. We know that that force has to be about that size because it's not moving. Well, as it turns out, most of you can guess that is a force from friction. there is a force of friction that when I push this way, it pushes back. A frictional force is a force that is between surfaces that are in contact. So this is very definitely one of those contact forces. If this block were not on the paper, there is no friction between the block and the paper. So frictional force is very definitely a contact force. What the frictional force is, the force of friction is a force that works opposite the applied force. So let's talk about some variables that change the frictional force, because you know this, you have experience with this. Some things have more friction than other things. First and foremost, if I have this block and then I put another block on top of it and I start pushing this, you know, the more blocks I put on here, the harder it is to move. I would have more frictional force when the amount of blocks increases. What I'm increasing is the weight here. But wait a minute, weight works up and down. Frictional force is working this way. And it's not really the weight that affects the friction, because imagine that these two surfaces were not in contact. Say I pick these up. Does this guy still have weight? Yes, but now there's no friction. The difference is we're not in contact anymore. Well, what was the force that was the contact force? It was the normal force. As it turns out, it's not necessarily the weight directly that affects the friction. It is the normal force, because you can still have weight and you don't have any friction. But the normal force pushing back from the surface puts it in contact. That's the contact force. Friction is a contact force, and it's directly related or affected by the normal force. Okay. Greater the normal force, more frictional force. Now, what determines the normal force? We know the normal force can change depending on the weight. So if we increase the weight, we increase the normal force, which increases the friction. But the weight is not changing the friction directly. So we know that's first and foremost, is the heavier something gets, the more friction there's going to be. The second thing is, what are you moving? What's in contact with one another? These blocks are a lot easier to move across this really smooth tabletop than they would be across even the paper or certainly the carpet. So these surfaces in contact really change the frictional force. Think about sliding something across a tile floor versus across the carpeted floor. The surfaces, even though it's the same object and you're given the same push, make a big difference. So the surfaces in contact greatly affect the frictional force. Now, there are actually two types of frictional forces. There is static friction, which means stationary or not moving. Then there is kinetic friction, which is moving friction. Have something sitting here. I have to apply a certain amount of force to get it moving, to overcome that static friction that is pushing against me. But if you ever move something really heavy, like a couch or a refrigerator or something across the floor, once you get it moving, it seems to be easier. And that's because the static frictional force is always greater than the kinetic frictional force. That's always true. So we're going to make a note of that. This is always larger. The static frictional force is always larger than the kinetic frictional force. It takes more force to get something moving than it does to keep it moving. The amount of frictional force can be, and we will calculate it. We will determine it experimentally as well. So we said it depends upon two things. One is the normal force. Two are the surfaces in contact. Okay. So we said the bigger the normal force, certainly the greater the frictional force. I get that. The smaller the normal force, the lower the frictional force. But how do we account for this? We're going to use the Greek letter mu. Looks like a U with a tail on the front end. This is called the coefficient of friction. What the coefficient of friction does is it tells you something about the friction between two different surfaces. And these have all been experimentally determined throughout history. It is a relative scale that tells you, okay, it's easy to slide across, glass or tile. So it has a low coefficient of friction. So the smaller that number is, multiplied by the normal force, the less your frictional force. Carpet would have a high coefficient of friction when it is up against, say, wood. And you would have a higher number, which would result in a higher frictional force. Now, these coefficients of frictions are something that are given to you. You look them up. There's a table, a book that has just an infinite number of coefficients of friction, because any two surfaces put together has a certain frictional value, that coefficient of friction between them. But we set up here that static and the kinetic friction are different. So how do we account for that? Well, there is a coefficient of kinetic friction and a coefficient of static friction, depending upon, is the something not moving yet or is it already moving? So to calculate the amount of frictional force, you take that coefficient of friction, multiply it by the normal force, and that will give you how much frictional force is working on that object. So on Monday, for our next class period, whenever that might be, you're going to be given a set of sample problems, and you're going to use this equation to calculate how much frictional force there is. And then we're going to label that in our free body diagram.